day, 7 days a week, 365 days a year, I'm going to be producing a video answering questions, common questions that engineers are asking, that they should be asking on ultrasonic transducers and piezoelectric device characterization, analysis, development, understanding. So today I'm going to start with a question about measuring the piezoelectric charge coefficient. Now, sometimes this topic and idea can be kind of confusing for engineers, and the reason why this can be confusing for them, because they calculate the charge coefficient based off of electromechanical resonance. So they do resonance frequency sweep. They use that to calculate the charge coefficient, and you get the coupling factor, and then you multiply over your compliance and your permittivity, and that's how you do it. And it kind of becomes a very vague or calculated parameter. It's difficult to internalize and understand. But in this video, we're going to go to the basic level. We're going to take a look at the constitutive equation. We're going to take a look at the basic level on how we go and understand what the charge coefficient is. So the charge coefficient, the piezoelectric charge coefficient, it exists in two dimensions. One is the direct piezoelectric effect, and the other is not the indirect. It's converse. The other is the converse piezoelectric effect. So direct piezoelectric effect, where you apply pressure, creating stress, and you get a charge. You get charges appearing on the surface due to the piezo effect. In the other case, you apply an electric field, and you get displacement from strain, and that also is related to the charge coefficient. Now, one question: is the charge coefficient from charge generation and displacement creation or strain creation, is that the same? Yes, it's exactly the same. And if you look at the units when we do when we are focused on generation of charge is coulombs per Newton. That's the unit of the piezoelectric charge coefficient, D. So coulombs per Newton. So you multiply newtons, you get coulombs out. That's charge. The other case is the converse piezoelectric effect, where you apply an electric field and you get displacement or you get strain. And the units for that, they're meters per volt. And if you do the equivalence of the units, you'll actually find them to be exactly the same. So yes, the same value relates both of these. So you can measure them in both ways, and theoretically there are some caveats. You can apply them to the different applications. So if you measure using a direct effect, you can apply that toward a you can apply that toward a system or an analysis that you're evaluating for the converse effect, which would be an actuator. So the direct effect is more of a sensor energy harvesting, and the converse effect relates to an actuator, where you want displacement, you're generating force, you're moving something. So let's get into measurement and how you actually go about measuring this, because I really believe that if you haven't measured something at a basic level, you won't understand it. It'll be hidden behind a veil. It'll be a parameter that you calculate, parameter that you're supplied with, but you don't have a really good interpretation of what it is. So let's start with measurement of the charge coefficient from the direct effect. And this is going to be pretty simple here. So let's say we had a piezoelectric material. This is actually a charger. We got 1 bar left on it. I've been charging this cell phone right here. So let's say this is the piezo material, electrodes on top and bottom. You press on this, and as you know, it'll generate a charge. By measurement of that charge, you'd be able to determine the piezoelectric charge coefficient. It seems kind of obvious, but let's listen to the equations here. So the charge over area, which is polarization, but charge over area that's generated on this surface is equal to the force over area, will equal to the pressure. So almost like that charge per unit area is equal to the force per unit area multiplied by the piezoelectric charge coefficient D33. We're just assuming the simple case with polarization in the thickness direction. So that relationship, once you figure out how much force you have, and you can obviously put your piezo material in a clamp, and then you could put a load sensor in series. You apply clamping force, you measure a charge, and therefore you have your relationship of the piezoelectric charge coefficient. The caveat here is that, why don't we do this more often? Why don't we just, seems pretty simple. Why do we have to buy a, expensive impedance analyzer in order to determine this quantity? Well, the impedance analyzer tells you a lot more than just the charge coefficient. But more importantly, why would we use cyclical electrical signals in order to determine these properties? The reason why you would use in two cases, why you would use a higher frequency to analyze your charge coefficient via resonator is because this property is slightly frequency dependent. Now, we ideally love to imagine that the properties are purely linear, but that's not actually true. Depending on the frequency of force you're applying, you're going to be changing your measurement. As well, the other case is it actually takes a couple of cycles for you to stabilize your D33 coefficient. So are you going to clamp it, unclamp, clamp, unclamp, clamp, unclamp? Don't unclamp it all the way, and don't go and consistently hit that amplitude. So it's a little bit more vague. But if you understand, and you take your piezo material as a true linear material, then that will more than suffice for your analysis there. What some devices have done in order to avoid frequency dependence, what some manufacturers, there are D33 meters with an alternating force. So it'll be like a buzzing, like two mechanical clamps, and it'll clamp onto your piezo material, you screw it down, and it applies an alternating force between these two clamps. That then allows for the cycling to occur, from which you can, it avoids that cycling issue. However, there are issues in mechanical clamping. As you're exciting this, there is some movement. There could be some motion based on imperfect clamping, and also the repeatability of mechanical holding interfaces. And also, you're just measuring in one area because you're only applying force in one area. So the other thing I'm going to speak about here, and before I leave that topic, how do you measure charge in this case? Because if you hook up your oscilloscope probe, they have their own capacitance to them, and they also have resistance. So you're going to start to drain your piezo once you connect it. So in order to avoid this drainage of charge, and that it's going to alter your calculations. In order to avoid this drainage of charge, what you're going to have to do is two things. Well, you could buy a very expensive equipment, charge. You could use a charge amplifier. You could use an electrometer with very high input impedance. You could also use with a very, very high large input impedance. You could also put a capacitor in parallel with your piezo, a capacitor much larger than the capacitor of your piezo element itself, because if that capacitance dominates, RC, time constant, because you increase the effective capacitance of the system, it's going to decay a lot more slowly. So you're not going to have near the rate of decay when you actually go ahead and measure it, and the voltage levels will be a lot lower too. So it'll be maybe perhaps more palatable to your multimeter or other device that you're using for measurement. So you can also introduce a series resistor, but I think just using that capacitor and relying on the large series resistance of the multimeter or your oscilloscope will be just fine. That'll allow you to calculate voltage. Q equals CV. The Q is the generated charge from your piezo, and the capacitor C is dominated by your parallel film capacitor. Let's put it in 5 microfarads, for example, when you have a 50 nanofarad piezo element, let's say. And your voltage measured is going to allow you to convert that capacitance that comes standard for that part, is going to convert that into a charge. Then you got your charge, you multiply by your piezo area, you have a force on the, you're applying your force, you measure that through your force sensor, and you're well on your way to getting the D33 coefficient. Charge per area equals force per area times D33. The next I'll explain, and I recently heard about this from a client of mine, a consulting client, that I knew this fact was true, that you can measure, and I've done it myself using a laser vibrometer. You can measure the piezoelectric charge coefficient by measuring displacement. So you can measure, you can apply voltage, you can measure displacement, and directly calculate the charge coefficient. This is, again, it's kind of many engineers that I talk to that I've told this to, they're like, why didn't I think of that? It's so simple. Like, obviously the piezo charge coefficient is the thing that relates displacement to an applied voltage or an electric field. Obviously that's the case, but it takes like a one step beyond just kind of knowing that behind the scenes to kind of bring it out in front of you and saying, hey, you can do this. It's much more simple than you thought. It's not a black box here we're dealing with. So the basic equation is that the electric field multiplied by the piezo charge coefficient equals the strain, and strain is change in length or divided by length or whatever distance you're sort of speaking about. And so the applied electric field of the voltage is going to allow you to determine that displacement. The only issue here is, let's say if you put 100 volts, 100 volts, it's not a whole lot, but it is significant. So you put 100 volts on your piezoelectric material. On a typical piezoelectric material, let's just pick a number down the center, 400 picocoulombs per Newton, 400 meters per volt, nanometers per volt. That's the unit. So if you take that unit, you actually get, for 100 volts, you only get 40 nanometers. So you're going to have to come up with a way to measure 40 nanometers of displacement. So thankfully, there are methods to do that. You can, so I'll give you two kind of methods there. So the first method that I want to give is if you use a fiber optic light displacement sensor. That is capable from, for example, for a company called Filtec is one of the companies, FILTEC. So that company produces a nanometer devices that can predict, that can measure nanometers of displacement. So you can directly get the piezoelectric charge coefficient from the converse effect, right? Directly get it from the converse effect. That's kind of a funny joke. The other way, the way I've actually done, so I haven't done that myself. It's just, it'd be kind of tedious because the probe has to get real close to the piezo. You got to have you have to have a very good positioning system. But the way I've personally done it is using a laser Doppler vibrometer, and I measured velocity. So from velocity, like let's say at 1 kilohertz, so way below resonance. So we're not doing resonance stuff at all right now. So we're specifically going to a frequency of 1 kilohertz or 10 kilohertz. You're applying your electric field or voltage. Now the displacement stays the same. You're flipping your electric field or voltage. Your displacement is going to stay the same because the amplitude of electric field is the same. However, because the frequency is increasing, the velocity increases. Because the velocity increases, you now have a nice big signal in order to measure. It's not that big, honestly. It's actually quite small, but it's big enough that on the lower settings, you can get something substantial for your measurement. So you'll be able to calculate a displacement, measure the strain divided by the length, and you are now on your way to determining the charge coefficient by yourself directly, without any barriers, without having to do a resonance frequency sweep and rely on too many equations. These are just basic equations you go through from the constitutive equations, piezo constitutive equations. So I hope you enjoyed this video. I'm going to be putting this is a YouTube live. I'm going to be putting a link to an article kind of talking about these, in this video I've talking about it, but also wrote up an article, yeah, I look forward to producing more videos. If you want to subscribe to my email and also get my PDF guide to the top 3 challenges of developing ultrasonic transducers, the top 3 challenges that engineering companies face, visit my website, ultrasonicadvisors.com, and find the link to sign up for my email list and receive the guide. I'll also put a link after this video is done. Thank you for those tuning in live. We got a couple of folks here. I look forward to making these videos. These are going to be done every single day. There's so much content I want to kind of put out there for everyone. And I'm just excited to get it out there. So I look forward to seeing you next time on the Shock Show.